It makes me happy that people are much excited about it. Dude. Realized the other day that I met Sam there. The first time meeting Sam, and I didn't remember because I blacked out, not blacked out alcohol, just don't remember saying anything. Yeah, I was so terrified. And then when you got like 30 balls on you, and it's like suddenly I don't have a brain. It ran away. Go where you sorry. It ran away. People are very receptive to it. I got people for 2 weeks afterwards coming up to me. I was like, whoa, so focused. I just didn't like people with the flag, right? I was like, hey guys. You said goodbye, it was funny business. Don't be weird. Yeah. I know. I'm so sad that it's not happening. I need to figure out how to send it it was one of those, but like there's something about Michelle. And it was like a funny accent, but she told me how to change. I like it's on the ground. I always get sort of this one. Even if the reason I pushed it's going down. It's very scary. Cute, my finger. You do like it. Yes. Nobody's got make anything. Make it hot me. See, I was thinking. These are all good. You don't. you just want me to look at what you do this time? Just the group actions, so.
Did you go ask those?
Yeah.
Yeah, I asked him last
That actually will like
No,
I'm not as a myself. So what you just said, I'm actually like I'm gonna look at this. I'm a single self.
Just today.
I'm good.
This morning.
Still are they gonna say the day? No. Maybe we'll just see sleepy.
It's actually terrifying.
All right, the homework's good today for that assignment. You're gonna be drawing the map for, segment coming from, adrenaline, right? The goal there is, you're basically sending a signal, it's basically to the liver, and you're telling it, hey, we're low on energy, we need you to release some sugar, release some food, right? So, you guys submitted that one. Check out to make sure you guys have a nice pathway, show off your receptor, show off that GAF function, right? Get into the TTP protein, hit the linear cyclic, and work down your pathway. On the other side, it was, we're gonna activate a different G protein. That was gonna get us with that, what do you think called PLC, or PLC? They call that? Also, there's like PLC, where PLC, we release the calcium and then actually they connect with each other. So I'm hoping your drawings have a nice connection with them, right? So basically this thing, right? So this is where we started, going this way at the AC of the cyclase, and we activate kinases. We're gonna stop right here. On this side, you're gonna have another G protein getting activated. Now we're sending the signal to that PLC. We're playing around with that molecule that has the PIM molecule, right? Which is the fats that go into the membrane, and then it has that nice sugar molecule. Right? It's gonna get extra phosphorylation, so normally it's 2 phosphorylations, you're gonna build up a third one. That molecule that gets released goes to the ER, throws out the calcium, right? This is gonna give us that second signal coming in. The phosphorylase kinase needs 2 inputs. It has to get phosphorylated, right? That's gonna be used and activated. The other one is this calcium is gonna bind to an allosteric site. So you guys remember an allosteric site is an enzyme, you can speed up its activity if you put an activator into one of those sites. So it folds a little bit better, you get a stronger signal. So having information coming in from 2 different sources, you basically make this system very robust, right? That's why both of them on, and both of them on, you get crazy on this. All right, so now we have our phosphorylase kinase. I'm really hoping that as you guys went through today's exercise, this heavy exercise, like trying to draw these things, figure out all the proteins, I want you guys to be noticing there was like themes of how these guys have been really working, right? So in your head, when you see the drawings, I want you to start thinking of some of them as like, hey, there's on pathways with our names, as long as I attribute a task to each part, future pathways are gonna be super easy to memorize, right? So here, if we go back to this one, and we're looking at that receptor, right? The glucagon's gonna come in. So in that case, we're working a little bit on this side, right? So there are two big words, the control rate's gonna be our GEF and our GAP, right? So GEF, what is it?
The guanine exchange factor.
Guanine exchange factor, right? So here, when the receptor is activated, that function is gonna be act as a GEF itself. What it's gonna do is, you're gonna have in your G protein, right? You create some units, currently it's stuck with GDP, right? AKA it's off. Nucleotide exchange factor, in my head, I'm thinking you're swapping them out. You're bringing in a brand new GTP, and this old one is getting ejected, right? Now you have an activated state, because it has GTP. In order to turn it off, this is where the gaps come in. What's the gaps? G, want to see mine? A,
Activating protein.
activating protein, yeah. This is basically, and this enzyme will try to hydrolyze this, right? So we're now having three phosphates stuck to each other. Like in my head, I imagine it's almost like you're having like a bunch of electricity, like they're supercharged. As it's doing functions, it tries to burn them off. There'll be proteins that come in and make this work a lot more efficiently. And that's just gonna end up having it burn off that first phosphate group, and it goes back to the GDP. Right? So GEF, we're swapping out one whole GDP molecule for a GDP for GDP. We're kicking one off, getting a whole one in. In this case, once we get to the gap, we still keep the same molecule, we're just kicking off one of the phosphate groups. Yeah. So prime, on, and then we can turn it off. AKA it'll be back to this prime state. Yeah. So right, that's what we're seeing here. That's what we're seeing there, right? It's like these proteins, if you can give them from GDP, they'll be off. Give them GTP, it'll activate them, they do their job. The next one we're gonna keep track of is gonna be like these, which would be like protein kinase A hitting the phosphorylase kinase, right? This one works a little bit like this. If we imagine our phosphorylase kinase, the purple one, let's say that would be my protein X, right? When it doesn't have any phosphorylation to it, it's on the off state or prime, it's there, but it's not really doing its job. The kinase comes in, this will be the protein that goes to it. From ATP, we'll remove one of these phosphates, and that'll be the one that it glues onto that protein. Right, so in this case here, this is our kinase, so that's the working protein. This is our protein X where we're dropping off that phosphorylation. Yeah.
So at that stage for the phosphorylase kinase, then you've now taken the calcium ions out through that channel.
Mhm.
And then how are you getting, is just the addition of the calcium enough to get it to the phosphorylase stage? Where it's like the activated glycogen phosphorylase?
I don't think so.
Okay,
Like if you're saying like we only have the signaling coming to this side, calcium shows up, we don't have the phosphorylation.
yeah,
I don't think it would give it, I don't think it'd be a functional enzyme to be able to.
okay, but then how are we getting from the kinase just to the phosphorylase?
From here,
Yes,
it's because this itself has to get activated by protein kinase A.
yes,
So when protein kinase A is the little purple bean that we draw in the class, it's being trapped by the repressor cell, right? So its kinase function is currently turned off. When cyclic AMP comes in, it removes the repressor, and now that thing's flying out as a kinase. We then go to this one, and it can phosphorylate. So ATP, it's the same trick. Kinase, all right, this will be protein kinase A. This will be, what did I call it? Protein kinase A, and this will be the phospholipase, right? It goes, it'll use ATP, strip one of the phosphate groups, give it onto that protein. Now this protein will be the active state.
okay,
And then when I want to turn it off, this is when the phosphatases come in. They'll come in, they work on the signal, and they'll take away that phosphate group, and now we're back to the off state.
Okay.
Yeah?
Yep.
All right. So whenever we're looking at stuff now, normally this is the big pathways of things we're gonna be looking at. I want you to be thinking in your head, is it a kinase? Is it a phosphatase? Is it acting as a GAF, or is it acting as a gas? Right? Today, that's gonna be the signaling pathway we're gonna talk about. We're basically doing like how we're gonna get energy out of the cells when we need it. This will be the pathway. This is your table. We're basically starting here the receptor signal is gonna come through. As I go through today's notes, I want you guys to be adding here. What's functioning like a kinase, right? What's functioning like a GTPase? If you do that, as long as you know this order and you know the jobs at each type, you basically can draw this thing out easily, right? I'm feeling pretty good. Makes sense? All right, cool.
Sorry, could you explain these again?
Oh, we're gonna go through this today. This is
Oh,
today.
okay.
But this is the pathway, like we're gonna start at the receptor tyrosine kinase, and we're gonna go down the line. But as we go through today, on your notes, I want you guys to add in, what does this follow under? Like, is it a kinase? Is it a phosphatase? Is it a GEF? Is it a GAP? Yeah. Once we have those notes, I think with just, like in my head, I would just memorize this, their functions, and I'm like, if you ask me anything, I could draw it for you in the test, no problem. Yeah. All right. And then the extra credit question, right? So we got me here. Kinase phosphorylates this guy, uses an ATP. Kinase uses ATP, phosphorylates the next guy. How does the phosphorylase get the sugar and add a phosphate group to it to break it down? Like, where does that phosphate coming from?
I'm just gonna try. It breaks the glycogen up into monomers,
Mhm.
and then in order to do that, there's an O link between each monomer,
Mhm.
and so it works with the OH group
Correct.
to basically like there's like an electron shift that kicks off one monomer to make it like a single unit of the glycogen.
Where does that phosphate come from? You just explain like OChem right now.
Like,
I'm
well, that's what I was
Yeah.
understanding. I was like, I understand how the phosphate is put in like chemically, but
Yeah.
where it actually comes from.
Oh, all right.
I found one thing online that said it was from phosphoric acid that's been condensed and gives a paradoxal 5' phosphate. And that's like the specific one that it uses.
All right. Where did you get your info from?
I sent you the links.
I haven't checked yet. So I'm thinking, when you guys answer this, if you guys got backup, if you guys got info from like a primary, like I went and found a research article, read it, and got the info, I'll give you 5 extra points. Google, Wikipedia, I'll give you 4 extra points, right?
Yeah.
So I'm gonna check your references and then
What if there's 2 sources?
2 sources, they're better. Like there's gonna be a
Yeah.
bunch of sources, because what's gonna happen is different cell types, different organisms might adjust their system might be just a little bit different from ours.
Okay.
So in that case, if you guys give me opposing answers, I'll let you guys argue, and as a class, we'll decide which one we want to put on the midterm. So even if they're opposing, I'm okay with it, as long as you back it up. Like we can't put, what is it? ChatGPT versus ChatGPT. I'd be like, no, guys, you gotta figure it out.
I thought it came from like when the ethylene cyclase turned ATP into CAMP as from your drawing, because 2 phosphates get put out. So I was just thinking that one of the subunits grabbed onto that, one of those free phosphates.
There, I tried looking it up. Did you find references for that one? Can you send them to me?
I did not. I
Okay.
tried looking everywhere, but I
Okay.
still, like, from your drawing, it's still like.
Because the moment you told it to me, I was like, we're on the right track, right? So it's like, from what I figured out, it's that, normally we call it like inorganic phosphate. Oh, we have it?
This is what I found. It catalyzes the transfer of phosphate groups from donors to acceptors, unlike kinases which transfer phosphate.
Correct, right? So normally here it's like, the phosphate is inside of a group, and we're breaking it off to go power up our reaction. In this case, so that's why I think Andy's right, I think you're right too, and you're right too, it's that you're basically grabbing a phosphate group that is kind of hanging out by itself, right? So in the sense of like, it's hanging out with a bunch of oxygens, right? It's not attached to a bigger molecule. We normally call those inorganic phosphates, And what it's doing is, in that step is, instead of being like here, where I have to bring in an ATP and cut it off, my drawing for that one would look something like, just like, right, this is our sugar molecule, like that. We're gonna break them apart from the other one. And as we do that, we're gonna produce this. And here it'll have the phosphate group like that. But the drawing would be that in here, this phosphate group at that would be shown like. One double bond. So it'd be a free phosphate group is getting kind of heated. So when it's a kinase, we break it from ATP. When it's phosphorylase, we're basically bringing in from like floating phosphate groups, which it could be from when we dissolve all that ATP to make that cyclic AMP. There we're gonna free up a lot of phosphate, so it could be coming from there.
So basically it just comes from cleaving the bond.
I don't know where they cleaved it from, that's what I was trying to figure out, but it is, the only thing that I was able to figure out is that it is a cleaved, already cleaved form.
Okay.
While in this case, when you're talking about these kinases, here, because each phosphate has a bunch of oxygen, you're using the energy from this molecule to kind of power the reaction forward. This phosphate showing up by itself is nowhere near the amount of energy that we have on this side. Yeah. So, let me give you guys flashcards, write your names on them. 1, 2, 3, yeah. So let me get the homeworks. If you have them on paper, I'll take them. If you did them on digital, I put a link up on Brightspace, you can upload them there. Please make sure you put your names on them, and then I'll take them by the end of the class. Or just drop them off for you guys to sit down. All right, with all that being said, let's tackle today's stuff. Everyone feeling pretty good about that pathway? Yeah? All right, you guys, all the steps, you guys feel comfortable, whether we're talking about a kinase, a phosphorylase, or a gap and a gap? You guys feeling good? All right, cool. All right, so more fun stuff, guys. We have more pathways on the way. This is gonna be a really good day today. For this one, we're gonna be, like I said, we're gonna be keeping track of energy. For this, that big marker of whether we have energy or not in our cells is gonna be that ATP molecule itself. ATP with 3 phosphate, they're normally unstable, but they represent a super high energy state. When we break off phosphates, we can release energy. As they do that, and they transition from this AATP to the AMP, AMP means a single phosphate group, aka we're at the low energy state, right? So we can actually use the concentration of those 2 molecules to gauge how our cells do. Are we high energy with a lot of ATP, or are we kind of low on reserves if we have a bunch of AMP? Yeah. With that, the major ones we're going to talk about, if we're low on energy and we need things to come out, we need to be able, there's different ways that we can get energy, right? We can get it from sugar, we can break stuff like amino acids, or the other one is we can break it from fats, right? When you're in an AMP state, low energy, normally it's time to catabolize, right? Time to start cutting things down and we take energy out of them. Right? At that time, you also want to think about, like, let's say you're low on cash, right? Almost like the AMP means you're low on cash. It's like you say, hey, it's time to make cash. It's not, you don't start investing or doing other, wild things with money. The cell's gonna do the same thing. It's gonna eat as much sugar, the fats, break them open, try to get things out. But at the same time, it has to be like, hey, I need to stop storing away fats. I need to stop making glycogen. I need to start making these bigger molecules. We're not cooking for a little bit, right? So I'll show you how to control that pretty cool. And that's gonna connect us to, we have the same thing where this low energy status is gonna activate let's cut stuff. It's also gonna turn off let's build stuff. And then we're gonna hit Anne's favorite stuff about translation. So it's gonna be good. All right, so again, the story there overall is gonna be when we're burning calories, we're storing macronutrients, you're putting any energy into the system or you're storing it. When we're eating, and this metabolism is breaking stuff down, is when we bring energy out, right? So the big one from like last time, it was this guy, right, which is when you have your sugars linked up in your long chains, your glycogen, we can't eat this, right? This can't make it into the mitochondria, we can't go through the whole glycolysis. Only when you break it down into something like this will be something we can automatically put into the bloodstream, we can send it across our blood to their cells. This goes right into your mitochondria, we're chopping this in half, we're breaking this, we're getting a bunch of ATP straight out of it. So when we're doing your storage of macronutrients, our cells are gonna grab these and they'll push them to make them like this. They'll be stored away in a safer format. When we're low energy, we're gonna go from this, cut them, put them into this state, and now we can take energy out of it. All right, so for this one today, we're gonna be talking about the AMPK signaling. So there we go, AMP, right, your low energy state, and it's gonna be a protein kinase. So AKA right here, your brain should be already lighting up. We're talking on this side, right? We're gonna see phosphorylations, we're gonna turn things on. The other one is gonna be these mTOR, which are mammalian target of rapamine complexes. It's the exact same protein. The only thing is, depending on who it's partnered up with, we had to call it complex 1 or complex 2, yeah? So let's go a little bit into the AMPK itself. So in this case, super complicated drawing for this one. The only thing that I really want you guys to kind of notice is we'll follow the 2 chains, right? Which is on this side. Super active, right? Here's your ATP state, you have high energy. As you're doing this activity, you're burning off that ATP, you're making that AMP. This is gonna be the signal that's gonna activate our AMP kinase. Now this is gonna act like a kinase, it's gonna go find these targets down here. And what it's gonna start doing is, again, adding phosphorylation marks to them. Those molecules are gonna turn from their off state to their on state, so they start doing their work. You don't have to memorize this guy, but we're gonna just follow this path. You activate your next target. These are then gonna be working a little bit, kind of like we see down here. They're gonna be working for us like GEFs. You're gonna come in, there's your RAB GDP. You have that function coming in. It's throwing us into the active state. All right, so make sense? Yeah. Active state, now we're gonna signal to these vesicles. This is actually gonna get us to dump out a bunch of sugar. The sugar can go into this cell itself. It can start sending it to the mitochondria, we start processing sugar, or we can kick it out, send it into the bloodstream, and we can get sugar to whatever muscle group we need to get to. Right, so AMP activates the kinase phosphorylates the next target. This target acts as a GEF. Now we have this new activated thing, and we can set the signal. Right? If I might ask this pathway. Right? I'm not gonna quiz them. I'm gonna bring them up right now just so I can show you different controls, but what's it called? You can ignore those on that side. It's just we have a lot of control coming from this. Like some of these, it'll be like mTOR is responsible for helping us create more protein. Right? So in the case of our regular cells, normally that signal's on, trying to make your proteins, you building amino acids, everything's good, you make your protein, right? The moment we have the signal saying, hey, we're starving, you don't have enough energy, this kinase will go phosphorylate the mTOR, but that phosphorylation mark actually turns it off. So now you've turned off a positive. So by doing so, you actually are gonna need to, without this, you're not gonna have protein synthesis. So low energy, you're gonna stop protein synthesis, right? So again, same thing here, we have one negative, like a negative arrow showing this is stopping this molecule from working, but that molecule is responsible for glycogen synthesis, right? AKA it's grabbing these sugars like this, and it's trying to glue them to make longer and longer chains. And it's like, hey, you don't have enough energy, why are you putting useful sugar over? So you need to turn that on. So just like that, we're gonna have multiple pathways that when they spread out and do this, they target different things that when they work together, it gives us a really robust system.
Does the ATP molecule, the brown one, function similar to the IP3 from the other pathway when it hits the vesicle?
Right, this one, right,
Yeah.
GTP? I'm not sure,
Or is it kind of like does it function as a ligand?
Probably gonna change the conformation of that, GTP. Yeah, GTP is. it's working at the membrane of that thing. And you'll see, I'll find some pictures of it with that receptor. It's probably gonna change, some of them, it's like if it's channels, it'll open up channels. In other ones, it's like the proteins on the surface will help you go find your target to dump out your content. So it might be working through like, kind of like guiding the vesicle to your target. But I'll put a quick note about that one on it. But again, the critical thing that I'm gonna focus on here is I want you guys to know that switch, right? Control of depth will get us here, and a gap will send us right back.
I have a question on the mTOR.
Yeah.
And then the GS, those are both turned off by AMPK. Is that what the red arrow means?
Correct, the red arrow, and also that it ends with a flat line.
So does that mean that it stops protein synthesis?
Correct, right, so it'd be like a positive signal would be like you writing right now, right? That's you being this molecule mTOR, and you're normally trying to do something positive, which you're writing notes, right? And then here would be if I am an AMPK and I'm being negative, and I'm like, hey, give me the hint.
Yeah, okay.
In that case, it's like, yes, you are a positive molecule, but my phosphorylation to you messed up your job, so you can't do it anymore. So these are super useful. You're gonna see them so much coming forward in the following charts. Give this expression to play with one right here. Yeah. So pointing arrow going from one thing to another is a positive interaction. I saw some guy has some really cool drawings. He does them like this. If the protein's in a certain state, let's say this is the molecule that comes in, it helps push this reaction forward, right? So it'll be the phosphate leaves. If there's something else that stops it, he puts in an arrow and he puts that flat line like that. And he'll be like, oh, there's a molecule that will stop this thing from moving forward. So they're super cool. They make diagrams pretty fast. All right, but here you can see one signal coming in, amplifies, but we've really started making sugar. We stopped investing in stuff that puts energy away. So here I did my little drawing. I added to their drawing a little bit of extra information. For this one, it's that AMPK. When we have that low AMP, we're gonna activate the kinase, and it's gonna send out a lot of this phosphorylation. It's gonna hit a lot of different targets. The main one I wanted you guys to take a look at was, again, emphasizing how the arrows work, right? So we're low energy, we need sugar. Glucose uptake is something that we want, right? Because AMPK, positive arrow, activates the glutamine or something like that. This one then is phosphorylated, activates this pathway, and will get us into this glucose uptake. So low energy, we're gonna absorb sugar into the cell. Critical, right? If we look at this case, right? So we're gonna look at glycogen synthesis. Glycogen is grabbing sugar molecules, gluing them together, basically putting your energy away so it's not accessible. This molecule is always trying to do that job, and PK comes in and tries to stop it. Right, so that was our example. If you're trying to do something good and I stop you, it's something like that, right? So we're turning it off by getting kind of rid of that intermediate. Back there we have fatty acid synthesis, right? So it's like, for this one, it's like the fatty acids, we can break them down and they make acetyl-CoA. Do you guys remember a little bit of acetyl-CoA? That sound familiar? So remember, acetyl-CoA is when you're breaking glucose, it's 6 carbon chain, you do a 3 carbon chain in the mitochondria, and then you break it down one more time to get your acetyl-CoA. So it's high energy. If you're making fats, you basically put it in the way, and you're breaking down the fatty acids, you get acetyl-CoA, you get high energy. So here, AMPK wants to stop at ACC1. That will we stop making fatty acids. So like we need to be acetyl-CoA available, so we can. And that's where we get to this really cool one at the bottom. Yeah.
No.
This fancy one. Right. So here, this is complete opposite example to Annie. Right? So Annie, she's trying to do something good, or she's trying to do something good, but I'm trying to stop her from doing something good. In this case, it's this molecule is doing something negative to the pathway, right? So oxidation means we're breaking down those fatty acids to make them so we can eat them. So that normally stops us from doing that function. What we'll do is When we're low energy, our molecule stops that molecule, aka it releases this and turns it on. Right, so it'd be like, if somebody's doing something bad and I stop them, then technically I did something good for that person, right? So we'll give you that example. Somebody's drinking, and then I'm like, hey, stop drinking, then your grades go, right? Or like, stop playing video games, and then you study more video games. So just like this, there'll be pathways. This first arrow is still the kinase function, right? We're phosphorylating with the molecules. This, they have their own little chains that we can draw out for them. Some of them will be phosphorylation, protein interactions, GTPase functions, all that kind of stuff. All right. But if I bring up a question about how they regulate, those four will be the ones I'm gonna focus on. Yeah. All right, now let's get into that mTOR. All right, so mTOR, here's that protein that I was talking about. It's the exact same protein. The only thing that really changes how it works is depending who its partners. Right? So it is the kinase, but here are the two big ones. If Raptor or Victor, you either have this mTOR, which is complex number 1, or that mTOR complex number 2. And what you guys are gonna notice is that within this pathway, when we're doing this receptor tyrosine kinase, we're gonna hit an mTORC number 2 first, and then down here, it's gonna be one of the last targets. You know? So let's get a little bit into it. So we're gonna walk our way through it, right? Right. These funny guys with the 2 little legs, right? These are single transmembrane part of that protein. We're looking at these receptor tyrosine kinases, right? That red part is where it does its kinase function. When we phosphorylate them, so when the receptor binds to its ligand on the outside, we then are going to activate the kinase function on the inside. So receptor, what word would you guys put here for this one? Right. What's that? How it's sending a signal forward? Right. So we're doing kinase function. Right. It's going to be adding phosphate groups to itself. That first phosphate group is going to help interact with that next molecule. This is that PI3 kinase. So the PI stands for that phosphoinositol, which is basically this little guy right here, right, which is the fat component that kind of sits inside the hydrophobic part of the plasma membrane, and then we have a sugar molecule sitting at the top. Right? In this case, what's going to happen is this PI3K is going to make it go from having two phosphate groups at 4 and 5, and then adds a third one right there. Right, so now it has one at 5, 4, 3, 2. Now it's activated. So this thing, we have another kinase doing the job, right? We're gonna phosphorylate those markers, those PIP2, it's turned into PIP3, because that's 3 phosphates. And now this signal is basically gonna bring in these 3 complexes, mTOR, C2, the AKT, and the PDK1, right? So in this case, this molecule being, or show it right here. PIP3, right? This goes to PIP3. PIP3 is only going to set up that next pathway. It's going to drag all these, that PIP3 is going to serve like a landing site or a place where it's going to recruit these molecules. It'll bring them all close together, and then we can have your mTORC2 and your PDK1 acting again like kinases, right? There you see your phosphorylation mark. Now that's going to be active. It releases from the PIP, and it goes and hits the next target. So here, kinase, right? And on that side, we have another kinase. At which point, now we're sitting here, right? Now this is where we have a funny loop here. So keep an eye on this one. It's TCS is responsible for stopping that red beam, right? Sorry, it's a double loop here. So if we go all the way down here, so I can tell the story, right? This red is regulated with that GTP. So if you imagine it's working on this side. It wants to go from the inactive state to the active state in VGTP. That's where TCS is going to stop that function, right? And it's going to stop it by acting like a gap. The cat's gonna interact with it, it'll help it kick off a phosphate, and it should throw it into that GDP state. So what we're doing is, if TCS is present, we're normally turning the signal on. So by having ATK come in and stop TCS, technically we've turned off a negative, and now we have a positive result. Does that make sense? Yeah. So at that point, if we have TCS not phosphorylated, I expect to see GTP, right? Because it'll be, so if this is TCS, no phosphorylation, that means that it's working as a gap, right? So AKA we should find GDP and the system's off, right? If this guy's phosphorylated, we've basically lost that gap function. So in this case, we're basically sitting over here in that GTP and we have a signal. Yeah. Once we do that, rev, nice GTP, it's doing its function. It can go and it then targets the mTOR complex number 1. This is the point where your signals divide, right? So we go down activating more kinases. And this is the important things. We start playing with protein expression signals, right? So they mess with EIF4. So we carry out initiation factors, aka you're making a molecule that stops a molecule that stops this guy. So when this comes on, this will be on, this will be off, aka this will be on, right? And then that's how you can translate to like, your translation will be on. If you go backwards and go, hey, this molecule's off, that means this molecule will be on, and that means that molecule will be off. Right? In that case, you basically stop your translation. That kind of makes sense? Yeah? You guys feel comfortable with the jumps with the negatives? All right, good. The other one is a little bit about how we talked about, if we're signaling, here's how we're getting connected right to protein or translation, how we're making the protein. But this signaling is coming from this growth factor. At the same time, there's other places that kind of come in and activate these things, like the AMP kinase, right? So remember, that was the one that if you're having a lot of activity, you get your ATP, you're burning it off, and you make a bunch of AMP. The AMP activates that AMP kinase, and then gives you that positive signal, right? So in that case, when you have low energy, TCS is basically going to get expressed very high, right? If you have a lot of TCS, we're going to kill this thing, right? Because we're going to have it all being turned into GDP. If that's the case, this is going to be off. Because this is off, when we go all the way down here, we're basically going to have, this is going to be messing up and stopping translation. In the other case, if it's a growth factor, and the cells are telling each other like, hey, everything's good, keep going, it's time to divide, that means that we have to make a huge investment in doubling our proteins, right, filling up our content. And that's where this pathway kind of takes over, does the opposite, because this is still here, and boom, we bring up translation and bump it up. Does that make sense? Yeah. This one, I feel like this is another one that I think is kind of interesting. I don't know what you guys think about it.
So if the AMPK is low energy, does that mean that AKF is high, or like the other one is when it's high energy?
Yeah, because in the other one,
That's AMP and that's ATP.
yeah, you're getting here, you're activating in the sense of like, your cells are talking to each other to like, to divide or to grow. And in that case, for you to be more functional, you have to have a lot more proteins. So the goal of this side is for you to walk all the way through, get translation work. In this case, it's like, you at that certain point in life, like of your cell chemistry, if you burned off a lot of your ATP and you only have AMP, you're low on energy. You can't invest energy in making proteins if you don't have enough to kind of keep yourself alive.
So you need to shut it off.
That's why you shut it off. Yeah. So that's what these signals will kind of be. They'll be at this point they'll be fighting each other, right? So it could be like, let's say I was sending the growth signals to you guys on the side of the class, but it's like everyone's okay. Everyone will start making more proteins, keep dividing. But let's say that Emma hasn't had lunch yet. She has no sugar, so then her body will be like, no, we have high AMP. We're not gonna waste time making this. Like we don't have the energy for it right now. And then she'll basically even though she got the signal, she'll try to stop herself from doing it. While everyone else will try to get it to happen. Make sense? Yeah? All right. So, to me, I liked the pathway you guys have drawn. I'm gonna look at your notes, I'm gonna give you feedback on it. For these other ones, I'm thinking I'm gonna make a few diagrams of them, and I'm gonna put them on the midterm. Like it'll be available to you guys, right? So you don't have to memorize exactly like, oh, ATK hits PDK or whatever. I'm hoping that you guys can use the arrows and the diagrams to decipher when stuff is behaving as a GTPase, or sorry, a GAP, a GEF, when stuff is a kinase, and when stuff is a phosphatase. So on your notes, I would go add this kind of stuff onto these slides to help you remember them, and then in the test, it'll be easier for you to make arguments with them. So yeah, you have a question?
Is the only phosphatase, or is the only one that acts like a phosphatase the TSC on that pathway?
Say it again.
Is it,
Wait, ask the question one more time.
is the only like molecule that acts like a phosphatase in this pathway TSC, or is there other ones?
So this one is acting like a gap. Right? So
Oh wait, I meant,
it activates the red protein. It's doing like a phosphatase kind of job where it's kicking off a phosphate, right? So it's doing that job that GTP, but that TCS is the one that's activating that function. But yeah, that's the only one that's doing this pathway, right? This job right here. The other ones, for the most part, our signaling cascade is it's kinase, it's a kinase, it's a kinase, it's a kinase. In general, we have a lot of like phosphatases who are basically turning these molecules off. So it's like this is kind of like a general mechanism of like, the signal isn't brand new, they'll try to turn it off. When a new cascade comes in, it'll phosphorylate that pathway, right? Like here, all these things will get phosphorylated, and then that signal will come on for a while, and our phosphatases will take it back. Now, unless we get a new signal telling us to keep growing, we're not gonna activate them. You know? So a bunch of kinases, and then here we have a gap. What's the question for this? Any questions?
So everything is a kinase except for the TSC.
Yeah. Ki3 kinase, the mTOR C2, and the PDK1, these two little arrows, kinases. ATK kinase, TCS is the gap. This one, I need to double check. I think it's a confirmation link between these two.
Okay.
Right. So
After the mTOR C1, those are also kinases.
for this one, here we have a kinase. I think this one will phosphorylate this, and I can't remember if the phosphorylation then helps it to be more functional, right? Because we're trying to have things to grow. What is that PIF for? But phosphorylation wise, I'm gonna quiz you guys from here up. Any more of these guys, right? For this one, I just like it because it's pretty cool of the negative feedback loops, where like you stop a negative to make a positive. Here I want to ask you how the modification works, but I do love bringing this thing up, like if this signal's on, would you expect this molecule to be present, yes or no? Like that kind of question. So again, I'll give you the chart and I'll ask you guys, this is off, what do you expect for this? Versus when this is on, what would you expect? You know? And then I'll do the same with like two positive arrows, it would be one plus, one minus. I'm thinking of doing that whole multiple choice test. So remember that I give multiple versions of similar questions on that test, right? So when you get this, don't automatically think, oh, it's the same question, it's on and off, right? So make sure you follow your pathway. I might go from here to here, from here to here, or from here all the way to there. And you should be able to be like, this is on, it's off, on, off. Walk yourself down the path. I'm feeling pretty good? Yeah? All right, what else was I gonna say? PTK. No. So So conclusion wise, what you guys think about two things, right? On this side, the main one is we're bringing in growth factors. The goal is we want to get all the way from here to make translation happen. On the other side is AMPK, we're low energy. At this point, we need to get energy out of the system, and the goal is we need to stop it from investing and making more purchases. So those will be our on and offs, our big on and off switch. Yeah. Hopefully we're good. Any more questions? No? All right, let me get those papers and then let's call it a day.